Hi, and welcome to module number 7 of the Practical AI in Healthcare course. I'm Dr. Sharon Basil. And this particular module, the topic that we are covering is statistics and data analysis using AI. So this activity is an accredited continued professional development activity under the maintenance of certification program of the Royal College of Physicians and Surgeons of Canada, provided through the University of Calgary. Now, this is my disclosure statement, and this educational content adheres to the national standards for support of accredited CPD activities based on the following mechanisms. Now, these are the topics that we are covering in this module, and this is really fun. That's why I went for a Pixar-like theme. And obviously, you can now guess this is created using Notebook LM. So now you will be, I think we covered it in the module number 4. So now we can create excellent infographics like this. Okay. Now coming back to the topic. In this particular module, we learns about the basics of basics and core concepts of statistics, including both descriptive and inferential statistics, with a specific focus on clinical research using an example from a neonatal ICU. Then I will try to be as simple as possible so that I know the statistics is a really boring topic. So I will try to make it as simple and as easy to understand. Now, and after that, we will be learning 3 different AI tools, which are Quadratic AI, Julius AI, and Gemini Copilot inside Google Sheets. And we will be learning how to do different types of analysis in a step-by-step format, how to check for the normality of the data, how automatically make the AI tool to tell you which all tests to be done to achieve the objectives. Then we will be learning the visualizations, like how we can create beautiful like pie charts, bar diagrams, then going to the advanced ones like QQ plots, then ROC curves, forest plots, box whisker plots, then all those amazing visualizations. And we'll also learn how to interpret the data based on confidence interval, p-value, effect sizes, and this interpretation will be automatic. AI will automatically tell you the interpretation. It will also tell you the what all things to be included in your results based on this interpretation in an academic tone. Okay, so this is really fun. So now let's proceed to the fundamentals of statistics. So let's decode statistics in an easy and fun way. Now, let's imagine a situation. You are working in an neonatal ICU in an institution, and you got 50 infants there. Okay, and you came across an interesting new neuroprotective agent with infants suffering from HIE. And you started applying, you started conducting a trial, and you observe that those infants in which this particular wonder drug has been administered, they are having fewer seizures. Okay. Now your question is, this is a result I am obtaining from this 50 infants, right? Whether in future I will be treating so many infants in this particular ICU, I will be treating 5,000 infants in future in the coming 2 years. So whether this drug will be effective for them or not, and whether the effect that you observed right now is real, or whether this is completely by chance, completely by coincidence. Okay, so that's the $1,000,000 question. So if you find that with high confidence, you can tell like this 50 infants are saved by, or that their seizure occurrence has been drastically reduced by this wonder drug. So I can confidently use this drug to the future 5,000 infants that will come to this NICU. Okay, so that particular way in which what we see in a sample and how it can be interpolated to a future unseen patients. So that comes the basis of our journey in statistics. So here, the one on the left side is the one that we know right now. Okay, so this is that 50 infants that you have treated using this wonder drug. And these 50 infants are called our sample, right? And based on this 15 infants, we got some data, and we represent this data in the form of results, in the form of tables, visualizations, like various types of interpretations of this data, right? So this is called descriptive statistics. Okay, so this is what we know. Okay. Now we are planning to generalize it to a larger population, generalize it to or universalize it to a larger or future population based on what we find. Okay. Based on our conclusion. That is called inferential statistics. We are based on our findings, based on our solid findings, we are confidently telling like I am confident that this drug can be applied with the same effect on some future population or future patient. Okay. And this particular logic that connects the what we have right now and what we will happen to the people in future or people in other places. Okay. So this bridge is called the logic of probability. Okay. So the test that you perform or the analysis that you conclude, the visualization that you make, everything accounts for this bridge. Okay. So the stronger your association, the better the test that you better the statistical test that you adopt for conducting this research, that will determine the strength of this bridge. Okay. Suppose if you are adopting a wrong test, or suppose if your analysis is wrong, then the bridge weakens and your generalizability is questionable. So that whatever that you obtained in this 50 infants may not be applicable to the general public, right? And it can result in so many complications, right? You will be wrongly giving a drug to a group of people based on your wrong tests and your wrong inferences, and that can affect the overall quality. So in a medical point of view, this bridge is really important. Okay, so in this particular session, we will be learning how you can build a strong bridge so that whatever you find in future can be applied to the general public and can be confidently published in a medical journal, in a high class medical journal, so that your authority in this field will be established. Like you will be able to find really interesting findings, right? So that's the basic idea. Now, what we really know, this part, okay, what we really know regarding this particular sample comes under the descriptive statistics, okay. So here we are not guessing or predicting, okay. So we already have some data with us based on what we saw in our NICU. So we clearly state these facts with perfect clarity. Okay, this is just like painting an accurate picture of whatever findings that we obtained regarding our patients in our present study. Okay, so this picture can be painted using any of these factors. It can be by visualizing data using scatter plots or histograms or pie diagrams. We will show that our data will show the central tendency, which will show what exactly our typical patient looked like and what was the key findings of our typical patients. Then there will be also will have some variability, like usually suppose if we have 50 infants, findings of all 50 infants may not be the same. Okay, there might be some slight deviations from the our usual results. The characteristics of the patients also will vary, right? So everything will there definitely our data will have some spread, but there will be some like aggregation of this data to the central area. So that is called central tendency. So now based on the data that you obtain or based on the data that you collect from these infants in your NICU, there can be three types of data. Okay, so the first type of data is called categorical data, which means the data will be in the form of groups or categories. So it can be like whether it's a male child or a female child, what will be the blood group of the child, or whether if the child is having some disease, whether the child is positive or negative for the disease. So everything will be in the form of categories like this. Okay, then comes a category called then comes a set of data called discrete data. Discrete data means they will be like in the form of countable numerical values, okay, with gaps in between. For example, heartbeat. Let's suppose if you are measuring the heartbeat, you will be measuring it in beats per minute, right? So it will be like a continuous set of not continuous, it will be like a discrete set of data. Then the number of hospital visits, okay, like that, or number of patients. So all these will be discrete data with gaps in between. And continuous data means it will be like a continuous stream, okay, measured in a continuous scale. For example, BP, weight of the child, or temperature of the child, everything will be in a continuous data. Okay, so these are the three different types of data. And the type of statistical test or statistical method that you use for analysis should be directly based on what type of data that you are having with you in an Excel sheet. Okay, so you have to use specific set of tests for each type of data. Okay, and that is really important. Now, the very cool part of the use of AI is like to determine which test to be conducted, test to be selected for this, you should have a clear cut or a very thorough knowledge regarding statistics, right? But most most of the time we may not be having that much thorough knowledge because we are not statisticians, right? We will be learning it on a at our free time. Like we don't have that formal training in statistics, so we can go wrong. Okay, but in that aspect, AI will come to your rescue. Like most of these AI tools, they are really thorough with the statistical fundamentals. So even if you are not that confident regarding the type of statistical test, AI will automatically determine the test for you. And almost in 99% of the cases, the test chosen will be accurate. Okay, because AI is really good with statistical analysis, especially tools like Julius AI. They can understand the normality, the distribution of data. We will be seeing what exactly normality is, and based on that, it can predict the best test for you. Okay, now comes the that central tendency part. Okay, suppose if you are have these 50 or 100 infants in your study, and you are looking for the head circumference of these participants, okay, of these patients, and if you represent the values that you obtained in the form of a curve, graph like this on a visual x-axis and y-axis, you will notice like majority of the infants, they have their head circumference in this central area, like they have a within a normal range, but there will be some extremes. Some infants will have a very like lower one, and there will be some extreme other end also as well. Some infants with extremely large head, right? But the number of such infants will be less in number on both the extremes, but the majority of them will be concentrated in this middle area. All right. So this particular representation is called a histogram, and this will on just by looking at the histogram, you will understand like how the that particular particular data is distributed. Okay. Now, if you look closely at this data, there are some interesting findings. Okay. So this type of distribution in a bell-shaped curve, this is called a normal distribution, and in this particular distribution, you will notice like 68% of the total participant will be lying within the central area. Okay, with this 68% area, and this is called one standard deviation. If you put one center line in this middle, and if you put one standard deviation to the positive side and one to the negative side, so this will comprise the total 68% of the total participant. And if you put one distinction here, so this is 2 standard deviation. This particular line is plus 2 standard deviation, and this is minus 2 standard deviation. Okay, so if you put that, 95% of the participants will be in this area. Okay, and if you put one more here, which is a 3 standard deviation, so 99.7 will be in this area. Okay, so this is the distribution, a completely normal pattern. Okay, but there will be some differences in certain scenarios. That curve may not be in this perfectly bell-shaped situation. Sometimes more number of participants will be located on this area compared to this, or more number of participants to be located on this area. So we will be seeing what are this deviation. So the importance of the bell-shaped distribution or the normal distribution or the skewing, that that distribution which outliers are more compared to the normal distribution, they are called skewing. So it can be more on the negative side or more on the positive side. So it's called a positive skewing or negative skewing. So that can affect the like overall quality of your data. So you have to choose the statistical test appropriately, accordingly. Okay. Now, for a normal distribution, the features are, it has a symmetric pattern. As you can see, if you put a like cross section here, it will be perfectly symmetrical, right? And it has a central clustering. Obviously, you can see the majority of the participants are located, or their values are located within this central area. And it has a tail behavior. Tail behavior means towards both the ends, it will be tapering. Right, so this is called a tail behavior, and it has a predictable spread. Predictable means 68% are within this first 1 standard deviation, and 95% are within 2 standard deviation, so on. So it is completely predictable. Now this is a normal scenario. Okay, now there are some values or some some calculations which will help you to identify whether your data is normally distributed and what's the average value. Okay, and this is called mean, median, and mode. Okay, the 3 types of this values that will be helpful for you. And mean means it's a mean value, and median means one that is locating towards the center, and mode means the most commonly occurring value. value in that particular set of variables. Okay, but some issues with this mean, median, and mode is mean is sensitive to the extreme value. Mean means it's average, right? So suppose if there are a few infants with extremely large heads, then the mean value will change from the center towards right side, because we have more values towards the right. When we take the average, naturally the mean will move towards the center. Okay, median means suppose if you arrange everything in a ascending order, the values that will be occurring in the center will be the median values, right? So even if there are some extreme values, either extremely negative or extremely higher values, the median will still remains in the center, right? So median is resistant to the outliers. Those with the higher values that locate towards the tail, they are called outliers. So median is resistant to that. Mode means the most common recurrent value. Okay, now these are the two different scenario. Okay, so you are having two sets of values in two different NICUs. Okay, and you are having a look at the mean weight or the weight of the infants who are admitted in that NICU. Okay, so in NICU A, you can see like it is following a normal distribution, right? So most of the infants, they are having their weights within this that particular range, like within 1 standard deviation or 2 standard deviation. Okay, but in NICU B, you notice like most of the infants are in the higher weight category, or I can say they are overweight. So you can see instead of the bell-shaped curve, you are having a curve like this. So this is the central middle area. Our median is located here in the original situation, but you can see this has been deviated to this right. So tailing behavior is there, but you can see the mean weight of the participants has been shifted towards the right side. Okay, so we can say this is positively skewed. Okay, this is normally distributed, this is positively skewed. Okay, the same can happen to the negative side also. There will be in NICU C, you will see there will be so many underweight infants. So instead of having a normal distribution, it will be like located towards the left side. Okay, so this is the situation. Okay, so if you look at the median values, mode values, and mean values, you can locate in this scenario, you can see this is towards the negative side. So mode is still in the middle, right? And median is towards this, and mean got pushed towards the another end, right? So towards when we have more outliers or more complex cases, these three values changes. Okay, so instead of having a symmetrical distribution, now it is having a right skew, or now it's having a left skew. Okay, now we comes to the other aspect. So so far we discussed regarding descriptive statistics, like what we already obtained. Okay, but now we want to extrapolate our result towards the general public or towards the future patients. Okay, so this is called inferential statistics. Okay, so but we have to tell with 100% certainty whether our findings will be reproducible, or whether our findings will be applicable to the unseen population, right? So for that, we need to know about three aspects. One is called hypothesis testing, whether to know whether this is what we obtained is real or not, or whether what we obtained is purely due to chance, purely due to coincidence. Then we have to know something called p-value, which will tell us like how much surprising our result is. Okay, and something called confidence interval, which shows what is the range of the true effect, like how well the effect is predictable, like whether it is a even though if the p-value tell like this is a real finding, but confidence interval will tell you like whether this is of any value or not, whether it's that particular effect has any main finding or not. For example, say in a simple example, I will tell you like you discovered a new drug for hypertension. Okay, so say the normal cutoff for hypertension is say 140. Say a patient's BP right now is 140. Okay, so your wonder drug is effective, and wonder drug can reduce your systolic hypertension from 140 to 138. Okay, so if you check for the p-value will be less than 0.05, telling like this has a significant finding. Okay, but from a patient point of view, reducing the systolic BP from 140 to 138 doesn't make any difference, right? Only if you are able to make a drastic difference, say you are able to reduce it by 20 millimeters, say millimeter of mercury, say from 140 to 120, you are able to reduce the BP of a patient drastically, then your drug has an effect, right? So then your confidence interval is better. Suppose if it's not able to make a drastic change, make the difference only by 2 millimeter, even if the p-value is telling like there's a significant difference, p-value is better, but the difference is not at all useful for the patient, then it's not a point to use the drug, right? So that's the difference between p-value and confidence interval. Okay, so confidence interval, the better the confidence interval, the better the effect that particular drug have for the patient, right? So that's the difference. Now, to test our finding, to generalize our finding, or to ensure that the finding is accurate, then we have something called null hypothesis and alternative hypothesis. Oh, okay. So think of this like a courtroom. Okay. So we initially we assume like, usually in a courtroom, like say you want to a crime has been committed. So initially we assume like the one convict has been caught and he has been put in front of the judge. So initially we assume like that particular convict is completely innocent. Okay, then the lawyers, they will tell the judge like, these are the scenario, these evidences are there, and based on this he is not innocent, right? So that's the usual proceeding. In the same way, we put it like a hypothesis which is called null hypothesis, and initially we assume like the drug has no effect. Okay, our new drug is no different from the placebo. Any observed difference is just random chance. Okay, so that will be our initial hypothesis. Okay, or this is also called innocent assumption. Okay, and we have an alternate hypothesis which tell the other way. Alternate hypothesis, which is called H1. The null is called H0, HO. Okay, I think H0 will be better term. And we will tell like our drug has real effect under the alternative hypothesis. The difference we see is actually real, and is not by chance. Okay. Now, objective of our analysis is to reject the null hypothesis and accept the alternate hypothesis. Then only we can tell like our drug has a true effect. Okay, and our job is to for our data is to provide enough evidence to the judge or to the general public or to a reviewer to so that we have enough evidence in our finding to reject the null hypothesis beyond a reasonable doubt. Okay, so initially we start with we have no effect. Our finding has no our particular objective is not obtained. Is not due to not understand the understood idea, right? We initially comes with we have our convict is innocent, or like that our finding is purely by chance. Then we will put evidence one by one. We have this p-value less than 0.05. We have so many significant findings like that. We put one thing after another, and finally we will reject our null hypothesis and we will accept our alternate hypothesis, telling like whatever finding that we obtain is purely not by chance. It's purely there is something like reasonable finding is there in our result. Okay, so that's the idea. Now, for this particular for establishing this particular thing, like our finding is not by chance, we have some reasonable finding, we need to have some value called p-value. Okay, so p-value varies between two extremes. Okay, so the cutoff for p-value is this one, 0.05. Okay, so if the p-value is higher, say p-value is at this location, the value is 0.5 instead of 0.05, then it's clearly show like whatever finding that you obtain is not surprising. Whatever that obtained is purely by chance. Okay, now if we reach the threshold of that p-value significance, that is 0.05, we can tell like after once it crosses that 0.05 threshold, okay, crossing the negative side, okay, when it goes down below that, we will tell the other end. We will tell like if the p-value is 0.01, we can confidently tell like our findings are really surprising. It is highly unlikely that this was just random chance. There is something really amazing regarding this particular drug. Okay, so if the null hypothesis is true, the drug has no effect. The p-value is a probability of seeing a result as extreme as ours. Okay, a low p-value means our result was a big surprise, making us doubt the null hypothesis. So that's the idea regarding p-value. So our study will become more meaningful if p-value is less than 0.05. Okay, now and one really important thing here is the statistical test that you choose for conducting this particular analysis is really valid. Okay, and that we will be coming to that later. Like depending upon the distribution of the data, we have to choose the right test. If you choose a wrong test and if you get a p-value less than 0.05, even though it's showing significance, but your test is wrong, right? So there is no point in doing that. So your entire analysis will be wrong. So your data is not generalizable. So you are getting some false results. So that also is a big issue. So we should be careful beyond that. Okay. Now comes the concept of confidence interval. Okay, confidence interval, it's the same concept that I mentioned regarding that hypertension scenario. For example, this is another scenario regarding intracranial pressure reduction. Okay, so here you can see one drug has been tested out, and we are finding a something like this is a scale in which we have a zero score. Okay, zero value, and there is a negative value. Okay, so we are testing out a new drug for reducing the intracranial pressure. Okay, so in the initial finding, we got a p-value less than 0.05. Okay, that is result A, and we found that intracranial pressure reduction, it reduces ICP by 5 points and up to 10 points. Okay, between 5 and 10 millimeters. Okay, and that's a relevant finding, right? But then in result B, we notice like that range is higher, so it can reduce the intracranial pressure from point. So in some patients it was 0.5, in some patients it was 14.5. Okay, so the effect is real, still real, but we are less certain regarding its precise size. Here we are more certain because the minimum we obtained is 5. So in all the patients we got a minimum reduction of 5 millimeter. Here in some patients we got only a reduction of 0.5. Okay, but in some we got a reduction of 14.5. So it highly varies. Okay, so the precision is lower here, but the precision is higher here. But in both the scenarios, p-value is less than 0.05. Okay, now in result C, our p-value was higher, much more than 0.05, and we also noticed like it is crossing the zero. Now it seems like in some patient, when you are giving the drug, instead of reducing the intracranial pressure, it is actually increasing it by 3 millimeter. But in some patients, it is reducing, and the reduction can go up to 7 millimeter. Okay, but it's actually causing the opposite effect, right? So which means that this particular drug has no effect. It can sometimes increase, it cannot. Sometimes it has zero, which means no effect. Sometimes it can reduce. So this result, actually you can straight away you can tell like this, we have to reject this result. So okay, so these two results can be taken, but between the two, this result is more reliable, right? So this type of results in which we are using a 95% confidence. Okay, and the true mean of reduction is between 5 and 10. So this result is more acceptable than result B. Okay, so that's the effect of confidence interval. So we should ensure like our results should be within the 95% confidence interval, so that the results or the findings that you obtain are more precise. Okay. Now comes the main part, like choosing the tool. Okay, so far we discussed regarding the p-value and the confidence interval. But suppose if the that statistical test that you choose is wrong, then everything is in vain, right? So this is determined by the like shape of your data, whether your data is normally distributed or whether your data is not normally distributed, whether you have the skewing and all. Okay, suppose if your data is normal, the distribution is normal, then you can definitely use a set of tests called parametric test. Okay, so this can be compared to an F1 car. Okay, you know, the results are highly accurate. I mean, for an F1 car, it is super fast. Okay, but the thing is like it cannot go through a bumpy road, right? So this type of tests are highly powerful and precise when the conditions are right. Like, you know, that F1 tracks are super smooth. There won't be any bumps. There won't be any gutters, right? So you can use parametric test. So the examples are t-test. Okay. On the other hand, if the data is not normally distributed, we can compare that to an off-road driving. So we cannot use such a car in this scenario. We need an off-road vehicle, right? So if you have a proper off-road vehicle like the one in the image, you will be able to navigate through that terrain without difficulty, and you will be able to reach the destination, right? So if you are using an F1 car here, I'm sure that we won't be even able to move 100 meters, right? You will be definitely in trouble. So that's the scenario. Okay. So bumpy road means the data is not normal. It doesn't follow a bell-shaped curve. It will be either towards the left side or towards the right side. Okay. So the terrain is completely rough, rough, right? So we will use a set of tests called non-parametric test. Okay. So the example of one such test is Wilcoxon rank-sum test. Okay. So these types of tests are like they are robust and reliable in case of scenarios where data is not normally distributed. All right. Now, these are some type of analysis you have to do to ensure like whether your data is normally distributed or not. Okay. Now, when I'm talking about regarding the data, suppose if you have a Excel sheet with all your data, if you imagine that, you can see there will be one on gender, there will be one on intracranial pressure, then there will be one on a weight of the infants and so on. Right? There will be so many variables. So we have to test the normality of each and every variable. So some of these variables will be normally distributed, some of them will be not normally distributed. Okay. So we will be doing a set of tests. I think it's given here. We will be doing a set of tests to understand whether the data is normal or not. Okay. So one of the most common tests is called Shapiro-Wilk test. Okay. And this will be usually done in scenario where your sample size is lower, if it's less than 50. Okay. Second test is called, this is very difficult to pronounce. It is Kolmogorov-Smirnov test. Okay. This is done in situation when your sample size is higher. Okay. But the problem is this is less sensitive. This is more sensitive. That's why we are using it for a smaller sample size. Okay. Then there is one more test called Anderson-Darling, but these two are the commonly done tests. In addition to that, there are two visual tests also. One is called histogram check. The other is called QQ plot. Okay. So these 4 tests will help you to identify the normality. Now, the good thing regarding our AI tool is like they can automatically do the test for you and can determine the normality. Okay. So otherwise, if you are doing it manually using SPSS or RStudio or Jamovi, then you have to do this normality test initially in the manual version and interpret the results and identify which all variables are normal and which all variables are not normal. Okay. Now comes the comparison between the parametric and non-parametric. So parametric is a F1 car, non-parametric is an off-road vehicle. Okay. So in parametric test, we do it for normally distributed data. The common ones are independent t-test, paired t-test, one-way ANOVA, Pearson correlation. And as I mentioned, these are more powerful and when the assumptions are met and highly precise. Non-parametric, on the other hand, we will be doing in data which are not normally distributed. And the common tests are Mann-Whitney, Wilcoxon, Kruskal-Wallis, and Spearman. And this is done in scenario where data is skewed. We have ordinal data, small sample size, presence of outliers, or when normality test fails. In all these scenarios, we will be using non-parametric. Now, this is the step-by-step process or how we will be proceeding in further sessions on how to do the AI tools for data analysis. Okay. Usually when you have the raw data with you in an Excel sheet or in a Google sheet and all, so some of the variables, some of the data will be having some issues. For example, say you ask for the like gender of the patient. Okay. So instead of providing a male or female like that, you instead of putting an option like a MCQ format, you put a fill up the blanks. Okay. So, and you will be telling the residents in your ICU, say you have 3 ICU. So there are 6 residents. So you tell the residents to fill the data. So when they are putting that, some of them, suppose if it's a female patient, female infant, some of the residents will be putting capital F female in such a way that F is capital. So it's a capital F, E, male. Some of them will put small f female. Some of them will put a small f just to denote it's a female. Some of them will put capital F and they won't be writing the full this thing. So you got, even though the question is gender, you got 4 variations of female. Okay. So in this case, if you are using a manual method of data analysis, you won't be able to analyze this data. So like you will, suppose if you create a graph for gender distribution, you will get 4 different variations of female. Okay. Which is not a good thing, right? So we have to do something called recoding. You have to convert all of them into a common format, whether it can be a common type of female, like word female, or it can be common F, or we can put 0 and 1, 0 or 1 and 2, 1 for male and 2 for female. So all of them will be recategorized into that this thing. So this method of changing your unclean data into a clean format so that this is ready to analyze, this is called cleaning. Okay. Now, if you are using a manual method of analysis using any of the statistical tools, you have to do this recoding manually. And most of this tool has some recoding options also, where you have to enter all the possible variations and what will be the final output, final coding format. Okay, but the good thing with AI tool is like AI tools, they automatically knows like a female can be represented in multiple variations, and all of them represents the gender female only. So the cleaning can be automatic. So that will save a huge amount of time. Like you don't need to go to the traditional statistics tools and then you need to define all the variables. Then you need to create a new variable like female gender recorded version. So it will take some time, but everything will be automatic irrespective of the number of data. Sometimes you have 10,000 data with you, and there will be so many different variables also, that all the cleaning can be done simultaneously with an AI tool. So it will save a huge amount of time for you. So the cleaning of data is a first step that need to be done. That will be automatic. So we'll see how the cleaning can be done using AI tool. After that, we have to test the normality. Okay, so we saw that there are 4 different types of tests available for testing the normality. So some tests can be used in certain aspect depending on the sample size, and based on that it will give you a p-value, and based on that you have to determine which all variables are normal and which all variables are not normally distributed. Okay, so we will do that as step 2 in an AI tool, which is again automatic. After that, say you are not that proficient with statistical analysis, statistical concepts of statistical test, and which all tests need to be done for obtaining objective 1, objective 2, objective 3. That time again, our step number 3 is asking the AI itself on now I have this particular data, this is the title, these are the objectives, you have already estimated the normality. Now based on these assumptions, give me which all tests need to be done to obtain objective 1, and which all visualizations are possible for objective 1. Okay, so automatically AI will give you an analysis plan. After that, we will in step 4, step 5 and all, we will tell AI to proceed with the above analysis plan in a stepwise format. Okay, so this is the modus operandi we will be following for the next two sessions, where how we will be using AI in to obtain accurate result. Okay, so that's the idea. And just remember this, like later on when you try out this AI tool, and sometimes you will be stuck, like even though you know the steps, in some steps you will be like completely confused on how to proceed. In that scenario, AI is like your best friend who is really knowledgeable regarding statistics part. Just give a prompt to the AI telling like, okay, I stuck here, you can proceed to the next step. Okay, so automatically AI will tell you like, okay, this is the present scenario, next step, next possible step should be this, shall I proceed with that? So it will prompt you regarding the next possible step, and you can easily proceed with that. Okay, so that's the idea regarding how we are planning to proceed with AI data analysis. This is really fun, and the best part is this is just like it is very easy to do, and this is completely beginner friendly. Okay, and very easy to understand, very easy to master, and you don't need that much thorough knowledge regarding statistics. So this is highly suitable for a clinician to easily do the entire statistics, and you will be able to publish in a high impact journal, because AI automatically will tell you like which are the advanced visualization, advanced test possible. Like it will tell you you can do a violin plot here. So you may not be familiar with the violin plot previously, but if you feel like, okay, violin plot is really interesting, if I insert that, the quality of my article will go up, right? And it will also tell you like we can put a box whisker plot here, which will looks really impressive. So again, we will put, okay, proceed with that. We can even tell AI like if after creating the box plot, we will tell AI, write, give me 3 sentences on how to write the explanation, which I can incorporate into my results. So AI will tell you, okay, I will write these 3 sentences as explanation, and you can just copy paste into your result and just modify it so that your results will be really strong, right? And suppose if you are sending it to PLOS, sometimes even if it's a simple study, the reviewers in PLOS will feel like, okay, even though it's a simple study, the analysis part is really excellent. You have so many advanced visualization for this simple study, so we will definitely consider publishing it. Okay, so it will improve your chances of getting published in a high impact journal. Okay, so that's the good part of using AI. Okay, so I'm sure that I have covered most of the basics. You got a clear idea, and let's proceed with analysis in the coming sessions. So thank you.